2 minutes, 5 seconds, and counting. After liftoff, we'll be listening to the voice of United Launch Alliance, Patrick Moore, providing ascent commentary.
155.
Launch sequencer start.
Minus 140.
FCS launch enable.
137.
CBC LH2 at flight pressure and flight level.
FTS armed.
Minus 120.
We'll see you armed.
FCS count started.
T minus 1 minute.
Engine start box go.
Rock, report range status.
Range grade.
50.
LCOVM. Third
Go,
stage is go for launch. Roger.
Range grade. Second stage LH2 secure at flight level.
40. Minus 30.
Status check.
Go Delta.
Go PSP.
Minus 15.
Profi ignition.
10. 9.
Sensor start.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
3R68 look good in the full thrust mode. "25 seconds into flight. Chamber pressures continue to look good on all three boosters. Now 35 seconds in. Chamber pressure on the core booster is throttling down to the partial thrust mode. Response looks good. Now 50 seconds into flight. Strap-on boosters look good in the full thrust mode. Core booster looks good in the partial thrust mode. Now 1 minute into flight. Vehicle trajectory looking good right down the middle of the range track. 1 minute, 10 seconds into flight. Coming up on 1 minute, 19 seconds into flight, max Q, maximum dynamic pressure, and Mach 1, Delta IV is now supersonic. One minute, 30 seconds into flight. Port and starboard booster engines continue to look good in the full thrust mode. Core booster looks good in the partial thrust mode. One minute, 45 seconds into flight. Trajectory continuing to look good right down the middle of the range track. ACS press valve has been opened. ACS pressure response looks good. 2 minutes, 10 seconds in. Strap-on boosters continue to look good in the full thrust mode. Core booster looks good in the partial thrust mode. And Delta IV has gone to closed loop guidance. Two minutes, 30 seconds into flight. And at 2 minutes, 39 seconds into flight, the Delta IV rocket now weighs just one half of what it did at launch, burning propellant at a rate of almost 5,000 pounds per second. And launch vehicle is now 33 miles in altitude, 49 miles downrange distance, traveling at 4,500 miles per hour. 3 minutes into flight. RS-68A engines in the port and starboard boosters continue to look good in the full thrust mode. Core booster looks good in the partial thrust mode. 3 minutes, 15 seconds into flight. Trajectory continuing to look good down the middle of the range track. Approximately 2 minutes remaining in the boost phase of flight. Chamber pressures continuing to look good on all 3 boosters. Port and starboard booster in the full thrust mode, core booster continuing in the partial thrust mode. And standing by for a strap-on booster throttle down momentarily. Port and starboard boosters have begun to throttle down. And we have jettison of both strap-on boosters. Core booster is throttled back up to full thrust. Response looks good. Four minutes, 25 seconds into flight. Upper stage lock system has begun boost phase chill down sequence. And 1 minute remaining in boost phase of flight. And upper stage fuel system has begun boost phase chill down. Five minutes into flight. Just over 30 seconds now remaining in first stage phase of flight. Core booster engine continues to look good in the full thrust mode. Vehicle trajectory continuing down the middle of the range track. 5 minutes, 20 seconds into flight. And standing by for core booster throttle down momentarily. Core booster has begun to throttle down. Standing by for BECO. And we have BECO booster engine cutoff, standing by for stage sep. And we have good indication of stage separation. NED is deploying. We have pre-start on the RL-10. And we have ignition on the RL-10 engine. Engine chamber pressure looks good. And we have good indication of payload fairing jettison. Now 6 minutes, 20 seconds into flight. And with the boost phase of flight complete, Parker Solar Probe will now continue its journey to the Sun. And it's 6 minutes, 50 seconds into flight. RL-10 chamber pressure looks good. Seeing good responses on the upper stage RCS system. And after a brief review of booster performance, seeing very close to nominal performance on the booster. And this first burn of the second stage will last approximately 4 minutes, 42 seconds. Now 7 minutes, 30 seconds into flight. About 3 minutes remaining in the first burn. And at 8 minutes 30 seconds into flight, RL-10 chamber pressure continues to look good. Seeing very stable values on the upper stage LOX and LH2 tanks. ACS storage bottle pressure looks good. And vehicle body rates are very smooth. Now 9 minutes into flight. And at 9 minutes 40 seconds into flight, just under 1 minute remaining now in the first burn of the second stage. Second stage continuing to perform nominally. RL-10 engine performing well. Tank pressures look good. Vehicle body rates remain smooth. Ten minutes into flight. And about 30 seconds remaining in the first burn. And standing by for MECO 1 momentarily. And we have MECO. Body rate smoothing out nicely. And now seeing upper stage ACS firings as expected. Now 11 minutes into flight. And this will be approximately a 13-minute coast duration prior to MES 2.
From the Mission Director Center, I'm joined once again by Alyssa Macbeth of United Launch Alliance. For those of you that are watching, we had an on-time liftoff today of the Delta IV Heavy rocket. And Alyssa, can you tell me how the launch went?
Oh my goodness, that was a beautiful launch. Just the sound and everything. Oh, it was great. It's looking good so far too. We saw good separation of the boosters from the main core and the booster from the second stage. Just experienced MECO 1. There's going to be 2 burns of the second stage, so that's coming up. The second burn, second engine start. And then in just approximately 45 minutes, we'll see payload separation. So everything's looking good so far.
Great. And can you tell me a little bit about your experience working with ULA and what it's like to work in a mission like this again?
Yeah. So I get to work with the innards of the rocket, the electronics, the avionics boxes, ordnance, pyrotechnics, all that kind of stuff. So working on a mission like this is something really special. To be able to get your hands on a vehicle like this and do something that's going to affect the world is really, really amazing.
Well, thank you very much again for being with us, and I think we'll talk to you a little bit later in the broadcast. Mm-hmm. Thank you, Alyssa.
Sounds good. Thanks.
And at 13 minutes into flight, Delta IV upper stage is continuing the coast period prior to MES 2. Vehicle systems all performing nominally during this coast, seeing periodic thruster firings as expected. Tank pressures and body rates remain stable. And a brief review of the performance from the first burn, seeing fairly close correlation on major orbital elements. Performance appears to be pretty good.
From the Mission Director Center, once again, we had an on-time liftoff of the Delta IV Heavy rocket. On your screen, you were seeing a live telemetry view animation of the rocket on its flight path. So things are looking pretty good at this moment as we're in a coast phase right now. And we'll go back to Marie Lewis for more on NASA's Parker Solar Probe. Marie?
All right, thanks, Josh. And I don't know about you, but here in the studio, we could feel the rocket rumble. And I know for our folks here on the TV side, that never gets old. We have Tori standing by now with a very special guest. We've been talking about him the whole show. And Tori, we can't wait to meet him. Please introduce us.
Thanks, Marie. I do certainly have a very special guest with me, Dr. Eugene Parker himself. Dr. Parker, you just watched the launch of the mission that bears your name. What was that like?
Well, I really have to turn from biting my nails and getting it launched to thinking about all the interesting things which I don't know yet, and which will be made clear, I assume, over the next 5 or 6 or 7 years. It's a whole new phase, and it's going to be fascinating throughout. I'm anticipating that the results will turn up basic information on why the corona of the sun is at 1 million degrees. That accounts for the acceleration of the solar wind. I'm just waiting for the data now, and the experts can get busy and sort it out, because there's an awful lot of data coming in, or will be a lot of data coming in. All I can say is, wow, here we go. We're in for some learning over the next several years.
That's right. So we'll definitely be anxiously awaiting that data and research. I also hear that this is the very first launch that you were able to witness with your own eyes. Is that right?
That's right. The video, of course, has supplied all of us with views of rocket launches, but somehow when you're looking at the real thing, it's quite impressive.
Nothing compares to the real thing, I would think.
Yeah, it's a little like the Taj Mahal. We've all seen pictures of the building and what a graceful structure it is, but if you happen to be in India and stop by that way, there's the real thing, and video and paintings and so forth just don't catch it somehow. Your mind is in a different state when you're looking at the real thing.
Well, we are certainly all honored to have you here with us this morning. Thank you so much for joining us.
My pleasure.
Marie, we'll go back to you.
All right, thanks, Tori. So great to have him here on the show. Understanding the sun will give us valuable information for future space missions. Mike Riskovich from Johns Hopkins Applied Physics Laboratory is live on set now with NASA Edge's Blair Allen. Blair?
Thanks so much, Marie. Listen, I got to tell you, I'm very excited, but I want to know, did you get out and see the launch, witness it firsthand?
Oh, yeah, I'm really excited. I had to run outside, and it was an absolutely beautiful night. The shock waves rolling over you, the beautiful sight of those 3 boosters rolling in. We could see it a long way. We could actually see the burnout, which was at about T+4 minutes, so really exciting night.
Now, what you work with primarily at the Applied Physics Laboratory is space exploration. How does a mission like this, we know the valuable science that it's going to get, but how does this help other missions with regard to space exploration?
Well, this is going to be a really big deal, not just for space exploration, but people on Earth. We're going to get a lot of new knowledge, which is going to help predictions and warnings of severe solar events that can take down the power grid or other pieces of our technological society. And then as we go ever more further into space, robotically or human, it's important to be able to get better forecasts and warnings for the operators of the robotic spacecraft and the people that go there. Today we're kind of like the mariners were in a few hundred years ago, where you didn't get warnings of hurricanes, and we want to be able to provide those warnings so we can keep people and hardware safe.
Yeah, exactly. Keeping our hardware safe, and all those future missions we have, and even some of our current missions will be able to help them as well.
Yes, no doubt. We try to design to withstand the harshest environment, but it's always worthwhile to have a good warning and know when you got to hunker down and play things safe until the storm blows over, so to speak.
Yeah, exactly. Well, I appreciate it. Thanks so much for coming off console to be with us for a few minutes and answer some questions. We look forward to getting great things from Parker Solar Probe.
Thanks. We look forward to it, too. We got a starting line and a finish line. Finish line for the development team and the launch team, and the starting line for the science team for 7 years of discovery. So,
awesome.
Thanks.
Yep. Back to you, Marie.
All right. Thanks, Blair. So how do we get close enough to the sun to actually sample its incredibly hot atmosphere? It's complicated, but NASA's Tori McClendon caught up with Dr. Nikki Fox, project scientist for this mission, to help illustrate Parker's path.
Thanks, Marie. Nikki, thank you for being here. You're welcome. So there's so many fascinating things about this mission. One thing that I find particularly interesting is the unusual orbit that Parker's going to take once it launches. Can you explain that?
Yes, once we're in space, it's a very busy first couple of weeks for us. We have to get it commissioned and all ready to go because just 6 weeks after launch, we encounter the planet Venus for the first time. We use Venus to give us a little gravity assist. Basically, it's like a little handbrake turn and it focuses our orbit in towards the sun because we don't want to be dragged around in any way or influenced by the Earth's orbit. And so during our 24 orbits of our 7-year mission, we actually will do these flybys of Venus another 6 times. And each time, as you can see from this animation, our orbit is getting smaller and smaller until those final 3 orbits, we are at our final closest approach.
Speaking of closest approach, can you describe exactly how close the Parker Solar Probe spacecraft is going to get to the sun?
Yes, at our closest approach, we will be 3.83 million miles above the sun's surface. And I realize that you just thought, million? That doesn't sound very close. Right. But the Earth and the sun are 93 million miles apart. And so if I put the Earth and the sun in the end zones of a football field, Parker Solar Probe would tuck and run all the way to the sun's 4-yard line, well in the red zone, knocking on the door for a touchdown, right by that goal line.
Well, that sounds extremely close to me. So I'm sure that folks are now wondering, how is a spacecraft not going to burn up at the 4-yard line?
We have a wonderful heat shield that we keep oriented between us and the sun. And so it keeps everything in the main body of the spacecraft nice and cool. It kind of creates a shadow. And it has a white coating on it that was specially designed for Parker Solar Probe, very much like you prefer to be in a white car on a hot day instead of a black car on a hot day. The heat shield is glowing and it is reflecting a lot of the sun's energy. And so the front side of the heat shield gets to about 2,500 degrees Fahrenheit, but everything on the main body in that shadow is at about 85 degrees Fahrenheit. So much like a pleasant Florida evening.
That sounds so lovely. Well, Nikki, thank you so much for being here today. We're all extremely excited about this mission. Go Parker Solar Probe. And with that, Marie, we'll go back to you.
We are coming up on another major milestone in Parker Solar Probe's flight. Let's head back over to Josh for the latest. Josh?
Thank you, Marie. I'm here again with Alyssa Macbeth, and we've been monitoring the flight as it's gone so far. And can you tell us a little about where we are now and what's about to come up next?
Yeah, so as I mentioned earlier, there was two burns of the second stage. So we're about to come up on that second burn. After that, the engines will light and we'll enter that phase, and then they'll cut off and we'll enter into a coast phase right before second stage separation. Then the third stage will ignite at approximately 37 minutes into the flight, and that will be our last and final burn before spacecraft separation.
So we had a great launch on time this morning at 3:31 a.m., but there's still more work to do.
There is.
Before the spacecraft separates.
Mm-hmm.
And can you tell me what's next for United Launch Alliance?
Yeah, our team is still working they're monitoring data in the launch control room and in Denver as well as here, just looking to make sure everything looks nominal, that the booster performed. They're probably looking at data from the booster and making sure everything looked clear and good there. And as we continue through the flight, they'll continue to do that.
Well, once again, you're looking at a live telemetry feed here. It's an animated feed that you see of the second stage. When at the very top of it, you see NASA's Parker Solar Probe there, which is moving toward its separation time. And we just have confirmation of ignition of the RL-10 engine. And with that, Alyssa, thank you for joining us today, and thank you for a great launch.
Thanks for having me again.
Yes.
Thanks.
Body rates continuing to look good, chamber pressure remaining stable. 24 minutes, 5 seconds into flight.
We are at a mission elapsed time of 24 minutes, 50 seconds into launch. The second burn of the RL-10 engine you see on your screen from the telemetry feed that is updated in real time. We'll continue to monitor things as we move toward spacecraft separation, where Parker Solar Probe will then begin to unfurl its solar wings. But for now, we'll go back to Marie Lewis in the studio. Marie?
All right, thanks, Josh. The Parker Solar Probe mission is designed to collect data and study solar processes that scientists have never seen before. NASA Edge's Blair Allen spoke with mission system engineer Jim Kinnison about the unique challenges in developing this mission.
Jim, tell me, what is the Parker Solar Probe mission?
So since the beginning of NASA even, there's been a desire to explore the regions around the sun, close into the sun, to understand the processes that are going on there, how the particles coming from the sun are accelerated, how all of that energy goes out into the solar system and even to the Earth and beyond. Parker Solar Probe mission is the final fulfillment of that vision. We'll be able to fly this spacecraft into very close regions of the sun, make those fundamental measurements by taking this approximately 10-foot long spacecraft with a nice heat shield on the front and keep it pointed in the sun to protect all of those things that allow us to make those measurements.
Why has it taken so long to get a mission like this together? Because I know this is all new technology.
So there have been some fundamental technologies that we've had to develop over the years, and there have been many people working for decades really to get those technologies in place. Some of those are things like the heat shield. Some of it is also in the area of developing the systems we need to control the spacecraft we're in those regions. Parker Solar Probe is a very autonomous system. It has to maintain itself without a lot of help from humans. So the ability to do that in space is really one of those fundamental technologies we've had to develop. We've also had to develop things like cooling systems for solar arrays so that we can power the spacecraft when we're close to the sun and maintain those temperatures that allow us to continue to make the measurements.
Couldn't you just use one really small solar panel for right when you get close and get all the energy you need?
So surprisingly enough, we actually do that. When we get close to the sun, we actually take those solar panels and tuck them behind the shadow of the heat shield until only the very tips of the solar array are generating power. So it's essentially that idea, yes.
I should have been an engineer.
Exactly.
Anyway, that's really awesome. Now, I understand we're going close to the sun, but you're not just flying to the sun. How is this mission oriented to get to the sun and get those measurements?
You're absolutely right. It's actually a fairly complicated process to get there. We'll be launching at a very large rocket to give us a lot of delta V that allows us to take out a lot of the Earth's angular momentum so that we can sort of fall into the sun, but that doesn't get us there. We actually have to do a flyby of the planet Venus and use our gravity assist to take more angular momentum out of the system so that now we can make that first approach around the sun. We'll continue to make several more Venus flybys, and every time we do that, our perihelion, the closest approach to the sun, will get closer and closer to that point where we finally are seeing the science that we want to see.
So how long is the Parker Solar Probe mission?
It's about 7 years to get the final set of data that we want to get. We'll be making 24 passes close to the sun in those 7 years, starting out at about 6 months for each orbit, and then down to about 3 months per orbit by the time we get to the end of the mission.
What happens after 7 years? I mean, are you going to get pulled into the sun, or could you operate beyond that if possible? Or
we will likely at some point run out of propellant, and propellant is the thing that allows us to correct for momentum and to point the spacecraft. Once we run out of propellant, the spacecraft will actually start rotating just because of the natural forces around the sun and the pressure of the sunlight on the spacecraft itself. And surfaces of the spacecraft which are not supposed to see the sun will see the sun eventually, and so that will have all sorts of effects that we don't really understand, and eventually the spacecraft will join the dust cloud around the sun.
See, that's why I asked the question, because Captain Kirk went around the sun and they actually went back in time. So I was just trying to find out if there was some extracurricular mission op that might send you back 7 years so you can get 7 more years of data.
He had the advantage of having warp drive. We don't have that.
Well, you know, something to put into development.
That's right.
Josh is standing by with a representative now from Northrop Grumman who has a big role in this mission. Josh?
Thank you, Marie. And we're sitting here continuing to monitor the burn that we have here before main engine cutoff 2, which is approximately about 8 minutes and 30 seconds away for the burn of that engine. And now I'm joined by Katie Nieves from Northrop Grumman. Katie, can you tell me a little bit about yourself and what you do at Northrop?
Sure. I'm a project manager for the Space Launch Program, supporting the Parker Solar Probe team.
And can you tell me what Northrop Grumman's role is with this launch?
Northrop Grumman Innovation Systems and sector and the divisions within it have really supported this mission tip to tail. Starting with the large composite structures, basically everything white on the vehicle, the nozzles, the fuel tanks, and certainly what I'm most familiar with, the third stage.
And right now you are looking at a live shot there. That's live telemetry that we're getting. The second stage engine continuing to burn, but after that, the third stage, the stages will separate, and then we'll have third stage ignition. And can you tell me what is unique about this mission for Northrop Grumman?
Sure. Every mission has its own personality and challenges to overcome. This mission in particular, the sun, gives a new element. So there's a couple of things to keep to take into consideration. The vehicle's trajectory is going very close to the Van Allen belt, and so the engineers had to create some rad tolerant electronics mass, keeping the vehicle as light as possible so that it could have the most performance is certainly a goal. And then I'm also told that this is the first third stage on a Delta IV Heavy. So those are definitely some unique aspects of this mission.
And so can you tell me a little bit more about this specially designed third stage?
Sure. Overall, it's about 7.5 feet long, and it weighs approximately 5,200 pounds. But it includes a Star 48 BV solid rocket motor. It includes flight avionics that's built on our heritage designs, which includes an onboard flight computer with navigation, adapter structures, and its own separation systems.
And so we're still continuing to monitor the burn of the second stage here, approximately 6 minutes left in that burn, and continue to talk about the upper stage. Has Northrop Grumman developed upper stages for missions before?
We have. Most recently, with the Star 48 BV, in 2013, Northrop adapted our Minotaur 4 vehicle. We added an upper stage to create a Minotaur 5 configuration for the LADEE mission that that went to the moon. And just last year, we had another Minotaur 4 out at the Cape on ORS-5 that was a uniquely designed upper stage for to perform a required plane change.
And once again, you're looking at a live telemetry feed of the spacecraft flying over the South Africa near the heart of VSTOC, which is the HBK that you see on the bottom right of your screen. And so, after this burn completes, we have a couple of events that are happening pretty quickly. Can you tell me about third stage ignition? How long this burn's going to last?
Yes, the Star 48 BV motor burns for about 1.5 minutes, and it produces over 15,000 pounds of thrust, which is about 20% of the total velocity of this mission, and about 60% of the overall orbital escape energy.
Has the Star 48 flown before?
It has, most recently on the LADEE mission in 2013, and then also our TACSAT 4 mission earlier in 2011.
And we just have about 4 minutes, 20 seconds left in this burn. And Katie, can you talk a little bit more about how Northrop Grumman has partnered with United Launch Alliance for this mission?
Northrop and ULA have a long-standing relationship that we're very proud of, and it's got different roles depending on the mission. Sometimes we're a customer, as in the Cygnus mission to the International Space Station. Sometimes we're a vendor, as in the large composite structures that we have provided for this Delta IV heavy mission. And in this case, we're very proud to be a partner with ULA and NASA.
We have about 3 minutes, 35 seconds left in this burn of the RL-10 on the second stage. We had an on-time liftoff at 3:31 a.m. Eastern of the Delta IV Heavy rocket with the additional third stage that we're speaking about now. The second stage continues to fly in its planned trajectory.
And about 3 minutes remaining in the burn. RL-10 chamber pressure continues to look good. Second stage fuel and oxidizer tank pressures remain stable. ACS press bottle also looks good. Now passing 35 minutes into flight. And at 35 minutes, 35 seconds into flight, approximately 2 minutes remaining until MECO 2. At MECO 2, the second stage will send a discrete command to the third stage to begin the initialization sequence. At that point, we should expect to start seeing telemetry data from the third stage through their transmitter. 20 seconds after separation of the second and third stage, the third stage will ignite, and it will begin its 89-second burn. Approximately 1 minute remaining until MECO 2. And standing by for MECO momentarily. And we have MECO main engine cutoff. Now passing 38 minutes into flight. Third stage transmitter is on.
And visual cue there of separation.
And third stage telemetry. And we have acquisition of third stage telemetry. And we did see ignition on the third stage, seeing chamber pressures, seeing some periodic dropouts of telemetry. Now 39 minutes, 30 seconds into flight. Should be expecting to see third stage burnout momentarily. Apologize, we're still seeing some periodic dropouts of third stage telemetry. Difficult to make calls. And at 40 minutes, 40 seconds into flight, still seeing some telemetry dropouts from the third stage. At this point, the third stage would have completed the burn and would be turning to the spacecraft separation burn attitude on a nominal timeline. Still looking for some data to confirm that. Delta flight commentary at 41 minutes, 56 seconds into flight. We are still experiencing some dropout of third stage telemetry, trying to confirm that the sequence of events, and we'll provide updates when that's available. Now passing 43 minutes into flight. And per a nominal timeline for today's mission, should be expecting to see spacecraft separation in approximately 1 minute. And we've been informed that the third stage is providing data to a ground station. Do not have real-time data, so we will provide updates of those events as they come in from a playback. At 44 minutes, 30 seconds into flight, still attempting to confirm occurrence of events for the third stage phase of flight. And per a nominal timeline, should have expected to see spacecraft separation within the last minute.
And you're looking at a live shot there, the Delta Operations Center. Team shaking hands. Teams in the Delta Operations Center shaking hands. Now the United Launch Alliance Mission Control Room. We have had confirmation of spacecraft separation.
Attention on Net 2, would like to confirm the spacecraft has acquired data, and we are working on a playback to get our third stage confirmation. But at this point, spacecraft is up and happy.
And confirmation of spacecraft separation there. You're looking at a live view inside the Johns Hopkins Applied Physics Laboratory where teams were just celebrating. And I'm still joined here by Katie Nieves of Northrop Grumman. And Katie, can you tell me what's next for Northrop Grumman?
Well, congratulations to the entire team. Best of luck for Parker Solar Probe. Coming up in the fall, we've got the Pegasus Icon mission right here in the Cape. We've got the Antares launch in November out of Wallops Island, Virginia. And then next year in April, we've got the Ascent booster test here also at the Cape, April of 2019.
Well, thank you very much for being with us tonight, and enjoy the rest of your day.
Okay, thank you for having me.
And once again, you're looking at a live view inside the Johns Hopkins Applied Physics Laboratory. We've just had confirmation of spacecraft separation, so the teams were pretty cheerful, pretty joyful in the room there. We did have an on-time liftoff of the Delta IV Heavy with the additional third stage this morning at 3:31 a.m. Eastern Time. But for now, we'll go back to Marie Lewis in the studio. Marie?
All right, thanks, Josh. In order to collect data for this mission, Parker Solar Probe is outfitted with several sophisticated instrument suites. NASA Edge's Franklin Fitzgerald spoke with project scientist Nikki Fox about the diversity of data researchers will study.
You're going to be collecting a lot of science data with Parker Solar Probe. Tell us about the instruments you're going to use to collect that information.
So we have a wonderful payload that was very carefully thought about and put together to make sure that we could make all of the measurements that we really need to do to answer these groundbreaking science questions. So we have 4 instrument suites. We have a white light imager, which we call WHISPER, that is going to look around the side and take images of the solar wind that is about to impact the spacecraft. And so it's really going to help us kind of unlock all our other measurements. We have the fields suite that is going to measure all of the electric and the magnetic fields that we want to measure, and also any waves, any signatures that happen to be embedded in the solar wind. We have the ESA suite that measures the high energy particles. So these are the kind of nasty guys that are associated with shocks and with flares and coronal mass ejections. And then certainly not least, we have our SWEEP suite that is measuring kind of the bulk solar wind. What is coming, what is hidden in the solar wind? What are all the different particle populations? What is the temperature, the velocity, the density? And so when we put all of those measurements together, we'll be able to answer our science questions.
Now, these suite of instruments, are they new, or are these off the shelf components that you use to build?
A lot of the instruments are very similar to ones that have flown before, but they are in very challenging environment. You know, for example, we have flown radio wave antennas on many missions, but not when they're going into 3 million degree material. We also have an instrument on the front of the spacecraft. I always refer to it as the bravest instrument because it takes no shielding, no protection from our amazing heat shield. It peeps out around the side. It's a simple instrument. It's a Faraday cup, which have flown on many NASA missions. But now we're asking it to work in this incredible environment. And so it is made with very exotic materials. And even though it's a simple instrument, boy, was that a challenging thing to get achieved.
Talk to me about the challenge of building that instrument to work in these extreme environments.
One of our biggest challenges is not even just the heat. So we're in 3 million degree plasma. Yes, that's awful and hot and dangerous. But our orbit is very much like the petals of a flower. So we go very close to the sun on one side, and then we come out around the orbit of Venus on the other, which means we go very hot and then very cold. Now, if you think of taking any material and heating it and cooling it many times, say 24, which is the number of orbits that we have, most of the time it will change its property. It will either become elastic or it'll become brittle, but it won't be the same 24 times later. All of our materials have to be the same. And so finding materials that would actually be able to withstand these changes was, of course, a challenge. And then testing them. The Parker Solar Probe spacecraft will be seeing just less than about 500 times the amount of sun we see here at Earth. So 500 suns in the sky is what Parker Solar Probe will be experiencing. And so how do you test it? We actually had to build test facilities just to be able to do this. We used reconditioned IMAX projectors because it turned out that the light that they put out is very much like sunlight. And so every single thing about this mission is challenging.
Well, can I go back to the IMAX projectors? Mm-hmm. What does that look like? How many projectors? What kind of facility do you construct this projector field to do this test?
So the original plan for this particular instrument was to use a solar furnace simulator in France. The problem there was that it only works during the day, and it only works if it's not cloudy. And so we couldn't get long runs to be able to get continuous hours and hours and hours worth of data. And so they actually constructed their own test facility. So up at the Smithsonian Astrophysics Observatory in Boston, they actually constructed basically a vacuum chamber, and then they took the 6 IMAX projectors and sort of chained them together, and so that would provide the right amount of illumination with the right amount of scattering angle for the light, the heat, and also firing particles at the same time to be able to really simulate what that instrument is going to see when we get very close to the sun.
Is there an opportunity for Parker Solar Probe to collect any science on its way to Venus and back to the sun?
So our intention is to have the instruments on it as much as possible. So we will have them on for the full journey in around the sun and the full journey out. The only time that we will not have the instruments on really is if we're doing a major maneuver on the spacecraft, or if we're sending our data down, when we need all the power to go into the system that is going to transmit the data, and so we switch off the instruments during those periods. I often get asked, are you going to do science around Venus? And unfortunately, my quick answer is always no, because whenever we are flying past Venus, that is our prime time to get our coronal science data down. And so the instruments are planned to be off when we do our Venus flybys. There is one later in the mission. We actually do 7 of them. There is one when the instruments can be on, and we are excited about what kind of science we'll be able to do then. But that's a number of years away, and few days away from launch. Everybody's focusing on the launch right now.
Where are you going to be for launch?
For the launch itself, yes. I will be honestly as close as physically possible to the Delta IV Heavy, but in reality, I will be somewhere around the press building, probably looking through my fingers at the site of the Delta IV Heavy. But actually, if they let me light it, I would.
I'm sure you would.
It's taken us 60 years to get through technological advances that will get us ready to launch Parker Solar Probe to the sun, as you saw a little bit earlier. And here's why it won't melt as it flies through the sun's corona.
NASA's Parker Solar Probe is a mission to explore the sun. How can it do that? Why won't the spacecraft melt? Excellent questions. You can't face off with the sun without packing the right gear. This is why Solar Probe is equipped with a white shield that reflects heat off the front and keeps things cool in the back.
The heat shield is made out of a couple of different materials. One is carbon-carbon, which is a lot like the graphite epoxy you might see in your golf clubs or your tennis racket, but it's just been superheated. The inside is a carbon foam, which is just another form of carbon and is actually about 97% air. It's a very lightweight way of making a very strong structure.
Nobody likes a needy explorer. Solar Probe can take care of itself, thank you very much. And that's because it has autonomy software that will keep its instruments safe and cool behind the heat shield.
We're too far away to joystick it into place, so it basically has to always be sensing whether or not the heat shield is in the right position and correct itself if it isn't. There are these things called solar limb sensors that are just poking out at the very edge of the shadow. And if those get illuminated, the spacecraft knows, oh, I'm, going the wrong direction, and can actually right itself.
It's important to stay hydrated in the sun, even for a spacecraft. Solar Probe circulates water to keep the solar cells from overheating. It stays cool and keeps power.
So basically, water flows behind the solar rays and into the radiators, and so the water warms up when it's behind the solar cells, and then cools down up at the radiators, and so that heat transfer is happening a lot like the veins in your body.
Yes, you read right. Heat is not the same as temperature. Temperature is a measurement, but heat is energy transfer. This matters because Solar Probe will be visiting the sun's outer layer, the corona. Like all stars, the sun is made of plasma. How tightly packed that plasma is depends on the layer. While the sun's corona has a very high temperature, the plasma particles are fairly spread out. So even though the temperature in the corona is 2 to 3 million degrees Fahrenheit, the heat around the spacecraft is manageable.
The corona and where we're going is actually not that dense at all. There are only a couple particles. And so when we think about it, those are very hot, but we're not touching a lot of them. It's the kind of like when you put your hand into an oven, and the oven might be at 400 or 500 degrees Fahrenheit, but your hand isn't at 400 or 500 degrees Fahrenheit.
Thanks to its design and destination, this cool, confident spacecraft is all set to explore. We can just sit back and chill as Parker's Solar Probe takes the heat.
We are now approaching solar array deploy, or when Parker Solar Probe will spread its wings. Let's go back to Josh in the Mission Director Center to walk us through this next event. Josh?
Thank you, Marie, and we are at a mission elapsed time of about 58 minutes and 10 seconds, and as you mentioned, we are waiting for solar array deploy that could happen as early as 12 minutes after spacecraft separation. That's a live shot. Everyone gathered around inside the Johns Hopkins Applied Physics Laboratory. We are standing by for an interview with NASA's launch manager, Omar Baez. He's going to talk more about this mission and how things went tonight. So we'll Wait not only for Solar to deploy, but also to hear from tonight's NASA launch manager.